Hey Calculus class! Today we're going to learn about topic 62, the comparison tests. So the first comparison test is what we call the direct comparison test. And this says that if you're given two series, A sub n and B sub n, where B sub n is a familiar series, where both sequences are positive. So that means all the terms in the sequences are positive. Some familiar series that we already know how to work with are geometric and the P series / the harmonic series. So in order to determine the familiar series, you will look at the given series and determine what series makes up its essence. So what I mean by that is if we look at these three examples, and at this first example, we have 2 over n cubed plus 3. And if we were to just kind of isolate part of this sequence, its essence would be this 1 over n cubed. Or we could use the 2, which it doesn't really matter. So we say that that would be our familiar series that makes up our starting series essence. I look at the next series, I would use the n over n squared as the familiar series. And in this specific case, we can go ahead and simplify this to get 1 over n, which is our harmonic series. And in our next one, the 1 over 3 to the nth would be considered our familiar series. When looking for the familiar series, you want to remember that constants don't really do much, and that the fastest growing element is your dominant series, which is why in this third series, I chose the 1 over 3n versus the 1 over square root n. 3 to the nth power grows much faster than the square root of n. So, if A sub n is less than or equal to B sub n, and the series of B sub n converges, then we say the series A sub n also converges. So graphically, this is what this is talking about. So you have A sub n as the smaller sequence than B sub n. And if B sub n is converging, it basically forces A sub n to also converge. If A sub n is greater than or equal to B sub n, and the series of B sub n diverges, then the series A sub n also diverges. So graphically, here we have the A sub n sequence, which is larger than the B sub n sequence. And if B sub n diverges, therefore it forces A sub n to also diverge. And just keep in mind that when you are doing this, the dominant series forces the other series to do what it does. All right, so let's go ahead and look at some examples of using the comparison test. All right, we're first going to determine whether or not this series converges or diverges. So we need to determine what familiar series this series is made up of. And it's similar to the 1 over n cubed, which we know converges because it's a P series where P is greater than 1. Now we need to show that A sub n is less than or equal to B sub n. So we want to show that this sequence is smaller than this sequence in order for this series to do what its familiar series does. So in order for me to show that A sub n is less than or equal to B sub n, I'm going to start off with the series that I want to be smaller, which is my original sequence. And if I was to tear back the layers or the constants that don't do a whole lot to the sequence, I would then get the 1 over 2n cubed, which would be a larger sequence than the 1 over 2n cubed plus 1. And then if I was to tear back the 2, I would get another sequence that is larger than both of the previous sequences. And I know that this sequence is larger than these two because as the denominator decreases, the fraction increases. So therefore, I know that a sub n is less than b sub n. So therefore, I can say that my original series converges by the comparison test with the familiar series 1 over n cubed. All right, let's take a look at this series. For the comparison test, the familiar series that I would look at is the 3n over 2 to the nth power. And I can rewrite this as a geometric series, 3 over 2 to the nth power. And since this is geometric, where the r value is 3 over 2, and since the absolute value of 3 over 2 is greater than or equal to 1, I know that this geometric series diverges. I now want to show that this sequence is bigger than the geometric sequence. So to do that, I'm going to start off with my original sequence. I'm going to tear back the layers so that I now get 3 to the nth over 2 to the nth. And as the numerator decreases, the fraction decreases. So therefore, I know that this sequence is larger than this one. So therefore, I can say that my original series diverges by the comparison test with this geometric series. All right, now we also have what's called the limit comparison test. This test says that given some series a sub n and another series b sub n, which is a familiar series, where both sequences are positive, if you were to take the limit as n approaches infinity of the original series over the familiar series, and if that equals if that equals some constant, where that constant is between 0 and infinity, then either both series converge or both diverge. In other words, if the terms of both series are growing at the same rate, then the two series will both do the same thing. And it does not matter which one you put on top. So, if I started out with the series n plus 1 over 3n cubed minus 1, and it is similar to n over n cubed, which reduces down to 1 over n squared. And I know that that series converges because it's a p-series where the p-value is greater than 1. So now, I'm going to go ahead and take the limit of one of the series over the other series. First, I'm going to do some simplifying before I attempt to take the limit. So I now have n squared times n plus 1 all over 3n cubed minus 1. Now if I went ahead and put in infinity for n, I'm going to get infinity over infinity. So I either have to do some L'Hopital or some magical algebra, and I'm going to do some algebra. So I'm going to factor out the largest exponent term between the top and the bottom, which is n cubed. And when I plug in infinity, these n's will cancel, these n's will go to 0, so I'm left with 1/3. So, since the series 1 over n squared converges, then this converges by the limit comparison test. So, because I got the limit to actually be some finite number, therefore, my original series will do whatever the familiar series is doing. So even if the familiar series diverges and I was to get a value out here, therefore my original series would also diverge. All right, let's take a look at this example. So this series is similar to 1 over the square root of n. So this diverges because it is a p series where the p is 1/2, which is less than 1, so therefore it diverges. So now I'm going to go ahead, put one series on top of the other, simplify it. I'm going to go ahead and simplify it again by dividing both terms on top by the square root of n to give me the following. And if I was to plug in infinity now, this piece right here will just be 1, but this one will give me infinity over infinity. So I need to go ahead and do L'Hopital on this term to get the following and simplify it. And I can go ahead and simplify the square root of n over n to give me 4 over square root of n. So now when I plug in infinity, I'm going to get a constant over infinity, which is just 0. So I'm left with 1. So since the limit does exist at some value, therefore the series does what the familiar series does, which is diverge. So therefore I can say that since my familiar series diverges, then my original series diverges by the limit comparison test. Well, I hope you enjoyed learning about the two comparison tests, and I will see you in class tomorrow. Have a good night.